All right. Hello, some of you. Hello, some of you, and hello, everyone else. I hope that you are all doing okay today. I know that you're probably all feeling rough, like with an assignment due tomorrow, at least in this class. I don't know what 2080 looks like right now. Is there another assignment due then? Monday? Okay, so kind of like the last time an assignment was due. So I get it, I get it. I hope that you are all actually doing okay, though. I hope that you're all doing okay. I hope you're all doing okay, especially despite the weather. Today, to open the class, I wanted to show you something. So this is the strings example that we've been working on for so long, and it still just prints out the character at A is 2. The character at 2 is A, and that's super not exciting, so I wanted to make it more exciting. And I've got this program installed on my laptop, and it's also installed in Aviary called Figlet, and it will make things like bubble font. And then I also installed the terminal text effects, and so now we can make this really exciting. Yeah, so the character at 2 is A is now at least marginally more exciting than it was before. Figlet is installed on Aviary, so if you want to have some excitement with this, you can also do that on Aviary. TTE is not installed on Aviary. I couldn't convince them to install that in time. But you can definitely have some fun with Figlet. That's a fun way to open this class. We're going to keep working with strings today. We are making like a literal one-word change to strings today. So we're going to do stuff with it, but we're making literally just one word of a change to this file today, to this set of files. We're also going to be using this example that's called badcomputer.c. You can find that in lecture 15 in the course content if you want to follow along with this. We're going to be using both of these examples as a debugging kind of target. I want to use this as a debugging target. So if you want to follow along with this, please make sure you got those on your system. If you are running a Windows subsystem for Linux, you might need to install an extra package to be able to do debugging. So the program that we're going to be using is called LLDB. If you're using the Windows subsystem for Linux, you may need to do something like sudo apt install LLDB. Or if you're running a Linux system, you may need to install this if you don't have it on your system already. We're going to start this pretty soon, so if you have one of those systems, try and get this installed before we get to that point. Alternatively, this is already installed, on Aviary, so you can also just connect to Aviary quickly if you want to follow along with what we're doing. I don't need to do this because I've already got it installed, but we're going to do some debugging today. So by the end of today's lecture, what I want you to be able to do is use a source level debugger such as LLDB to inspect program state and step through code line by line to determine the cause of errors in a program. We're going to be looking at this from two perspectives. I want to look at this from the perspective of code that crashes. So we've got some code, it crashes. We maybe don't know why the code crashes. What can we use a debugger to help us with in that situation? The other thing that I want to use this for is we have code that doesn't crash, but I want to understand how the code works. So I want to use LLDB to step through a list structure that we've built up, and that's where strings comes in. I also want to use LLDB to make changes to the state of our program as it's running to like violate assumptions and cause assertion failures. And then we can use that as an exercise to see what happens when we've got this assertion failure. How can we go back and see what's going on with things? So we're going to do this today. The other thing that I want to do is define the implementation of an ADT with a private data structure. This is a continuing learning outcome. And really specifically, I want to use this keyword static. Static is a keyword that you have 100% seen before. I know that everyone in this room has seen this before because you've all written a main method in Java. Public static void main string args. There's static right there. We're going to talk about what static means in C. It's not exactly the same as what it means in Java, but it's kind of close to what it means in Java. So we'll do that. And then the other thing that we're going to do, I didn't list this as an outcome because I don't actually want you to do it. but I want to show it to you anyway. We're going to think about using something called extern to share data between files and between libraries, but I don't actually want you to do that, so I'm just going to leave this not as a learning outcome for today's class. So let's talk a little bit about debugging. You are in a state where, so put yourselves in your mind theater right now, you're in the state where you have either written some code, and maybe it was long enough ago that you don't really understand how it works. And if you're anything like me and past Franklin, our relationship is fraught sometimes, where I code stuff and I don't really comment it very well, and I try to be tricky with things, and then I don't really understand how it works anymore. Maybe you and your past self have that same terrible relationship. You're in a state where you've got some code that you wrote and you just don't understand how it works anymore. And then also maybe you never understood how it worked. And I mean, I've done a little bit of this sometimes where I get something from somewhere else, not necessarily ChatGPT, but I never really understood how this worked, but it solved the problem I had at the time, and I was just happy to use it. And it doesn't work. I've got it. I know that I wrote it at some point or had some help writing it at some point, but it doesn't work anymore. Another situation that you could be in is that someone has given code to you. I'm sorry, you've written code and you give it to someone else. And they compile it, or you compile it for them, and they immediately make it crash. They find some way to enter an edge case into your code, and you didn't account for that when you set things up. Or alternatively, you've been given code that's been written by somebody else, and they didn't understand how it worked, and it crashes. What do you do? This is like the situation that we're in. We've got some code that we don't completely understand how it works, or we've got code that crashes. The approach that I'm going to suggest is a few different things. One of them is spelunking. When I'm using the word spelunking here, spelunking is literally cave diving, but I'm going to be using this in the context of code. Using assert, so taking the assumptions that we've got about code and encoding them in the code that we've got. Using printf as a tool to help us solve problems. And then something else. And I might have buried the lead at the beginning when I'm talking about debugging, but there's something else here. Spelunking here is literally just going through the process of, you've got this code, I'm going to spend some time reading the code. I'm going to spend some time reading the code and then trying to mentally keep track of the state that things are in. And maybe this means that you've got a pencil and paper and you're going through and you're writing down names of variables and what their values are and stepping line by line through the code, all entirely in your head. As you're doing this, one of the goals that you've got is to try to identify the assumptions that are being made. So this is all the design by contract stuff that we've been doing, but doing it after the fact. As I'm stepping through this code, I'm identifying that maybe there was an assumption that this value that's being passed to this function should not be null, but it's not actually stated anywhere. Maybe there's a range that this value should have, but it's not actually stated anywhere in the code. Maybe that this object has an invariant. There are properties that it must have at runtime for it to be valid. As you're stepping through and reading this code and executing it in your head and coming up with these preconditions, postconditions, and invariants, then once you've got some basic understanding of the code, take those assumptions and begin to encode them. So start to make changes to the code using assert, the tool that you've got to enforce these preconditions, postconditions, and invariants. Apply them, try again, see if the code still crashes in the same way that it did previously. And the goal that we've got with assert is that we're trying to get a better understanding of the state of the application. This application state here is the value that all variables have in a running program while a program is running. And this is something that we're usually measuring at a specific line of code. So while our code is running, at this point in our code's execution, variables will have this specific value. When I'm thinking about application state, I'm thinking about all of the variables that are in the code at that time. You do this, you add these assertions, you're trying to get this idea of what the state of the code should be, you're trying to enforce the assumptions that you've got. But now you're in a state where you run it and it still crashes, but not because of an assertion failure. So you tried to come up with all these assumptions, but you really weren't able to identify what the assumption was that's being violated that causes this thing to crash. If this isn't code that you wrote originally, you might not even really know like what that person was thinking when they were writing it. Again, if you're like me and you've got that bad relationship with your past self, maybe you don't know what you were thinking 2 months ago when you wrote this code in the first place. Despite adding assertions, the output that you're getting from some code is still segmentation fault, or it's still not what you were expecting it to be when you had intended to change it with assertions. Our next hammer here, our next tool, is to start using printf. The idea here is to start putting printf statements in our code. And the idea here is to not really to like print anything meaningful out, except for us to be able to find out how our code is going from one place to another. Put a bunch of printf statements in the code and see where the printing stops. The goal here is to try and get a better understanding of the flow of the application. So assertions and reading are trying to help us get a better sense of the state of the application, so what value variables have at any given time. Application flow here is how our computer is moving through the code in our applications. How do we flow from main down to this other function where it's actually starting to crash, or where we think it's starting to crash? How do we get from here to there? And then how do we go back again? One of the problems that we have with printf that's unlike system.out.println in Java. So I'm confident that all of you have used system.out.println in Java to try and figure out why you're getting a null pointer exception or an array index out of bounds exception. And that works great in Java. It works great in Java. The problem in C with printf is that printf is buffered. So I've used this word before to call a buffer an array. I've tried to make these synonyms. Buffering here means something slightly different. It's kind of talking about the same thing. Printf puts stuff into an array, a buffer, but it doesn't immediately print to standard output when it does that. We could force our operating system to write after every printf, but that's kind of tedious, and I don't really want to do that. I want to put this into action. So I want to take a look at badcomputer.c. Here's badcomputer.c. It defines a function called substring. It takes as input a string, it takes as input a start, and it takes as input an output parameter called out. In this code, we're declaring a string. We're declaring a buffer, an array, where we're going to write to on line 25. We're printing out what the string is on line 27, calling the function on line 28, printing out a message on line 29 that says this is what string is and this is what the destination is, and then exiting on line 30. The substring function itself has its preconditions asserted. It's got a loop that goes through the process of copying from one string to the other, starting at a location, and then it terminates with a null byte, and it encodes its post conditions at the bottom here. I believe this is a reasonably well-written piece of code. If I run this, I want you to mentally think what you think the output from this code is going to be. I'm going to tell you right now that this code crashes. It does crash. And I'm going to tell you where it crashes. It crashes after returning from the substring function. It takes just a second to think about this. Take 30 seconds looking at the main function, what you might expect to be printed out from this code. This code compiles with no warnings. I'm going to run it, and it immediately segmentation faults. I'm verbally telling you that the error happens after returning from substring. But printf didn't print anything, despite being before calling substring. Printf is buffered, and the way that printf does buffering is that it says, if there's no new line in the character, I'm not going to print out a line. I'll print out a line when I see a new line. So I'm going to add a new line to this code, and I'm going to add a new line here. Oh, there's already one there. I'm going to recompile this code, and I'm going to run it. And now, on line 27, we print out string is. This is a really long string, like super long. I still don't understand what domain expansion means, but here we are. And then it's segmentation faults. Okay, that's good. That's what I was hoping for. The problem that we have with this is that if I redirect standard output, okay, on the count of 3, on the beat after 3, I want you to say greater or lesser, greater or lesser, to say which of these two operators I should be using to redirect standard output. We got that? Greater or lesser. So 1, 2, 3. Greater. Good, greater. If I redirect standard output, I'm not expecting it to print anything to standard output anymore, because I've literally just said redirect this output to standard, redirect standard output to a file. My shell says that this program ended with sig_seg_v, segmentation fault. I still expect to see that output.txt will have something in it, but it doesn't. So I've added this new line character. When I run this on the shell, it prints out that message, and I can follow that message to say that it got there. Printf is smart enough to be able to say, the thing that I'm printing to is an interactive thing. I'm expecting that somebody might be typing stuff on the end of this. So when I print a standard output that is my shell, it's able to print the message because that's an interactive thing. There are human eyes reading that. But it's also able to see when I redirect to a file, that is not an interactive thing. Human eyes are not reading that right now. They might later, but they're not reading it right now. So if my redirected standard output gets redirected somewhere, the message that helped me find before where the code crashes suddenly is not there. So that kind of leads us to this point of what do we do? And this is my answer to that. I don't know if you've ever seen this show called Adventure Time before. Has anyone seen Adventure Time? Some of you have? Yeah, okay. When this show came out, it was kind of like, this is a stupid, funny show. Like, Finn, this is the boy that's sitting there. He is battling the Ice King, who lives in an ice castle in a mountain. And the dog is called Jake, and Jake has these like crazy powers where he can just like stretch out like crazy and turn into all sorts of stuff. And it seems like it's really stupid funny. Oh, and this computer is called BMO. And BMO is sentient computer that has batteries that it has to change every once in a while. And like on the back, it's kind of like a little Game Boy, and you pop the back off. And so when BMO needs to change batteries, it pops the back off, pulls the batteries out, and then briefly dies, and then falls onto new batteries that it's placed on the ground beneath it. When this show came out, it was really kind of just like stupid funny, but then if you keep watching it, and all the episodes are like, they're quite short, if you keep watching it and keep watching it, the backstory gets really deep, like really deep, really, really deep. And I don't want to spoil anything, but eventually it's kind of revealed that this is a post-apocalyptic Earth. And like there's magic in this post-apocalyptic Earth. And it's a really deep story. And then there's a spin-off called The Adventures of Fiona and Cake, which is an alternate universe that sits beside this one, where Finn is a girl and Fiona's sidekick is a cat called Cake. And the Ice King lives in both universes, but in the Fiona and Cake universe, he's a guy named Simon, thank you. Yeah, Simon. Okay, so good. Someone's watching this show. Awesome. When you have lots of free time, please find and watch this show. It's worth it. I really, really like it. So what then? Yeah, yes. No, I did not see that. Okay. What is this? Like a game? Is this a legitimate game? Like with licensed characters? Okay. Okay, I will see if I can check that out. And it's free. Oh. Okay, well, I'll see if I can check it out. Okay, so what then? We don't have BMO. BMO is not our computer. I'm not going to hit BMO with a newspaper. I'm not going to hit my laptop with a newspaper. So what then? We're going to use a source level debugger. A source level debugger is a program. This is a separate program. We wrote some software. A source level debugger is a separate program that's going to run our program. It's a program that we can use to step through the code that we've got line by line. We can observe the flow. We can see the application flow. Where printf is buffered, a source level debugger is going to let us see which line is running next. We're going to be able to watch variables as they change. We're going to be able to see things in the code's application state. We're going to be able to observe the application state as we step through each line of code to see how things are changing, and we can inspect what the value of variable has. We can also cause execution to stop at certain points. So we can choose to run our program line by line. We can choose to say, I want you to run up until you get to a point. If we're using this in an advanced way, we can say, I want you to stop when you get to this point if a condition is met. So I want you to conditionally stop at a certain point. This is called a breakpoint. We're going to use LLDB to do this. When we're compiling our code, we must add a new flag to Clang. So the flags that we've been passing to Clang so far are WALL for warnings all. We've been passing -C to say just compile this, run the assembler, but don't link it with anything. We've been passing -O to say this is the name of the file that you should be producing. The -G flag says compile this program, but also attach the source to the file so that I can use a program like LLDB to step through the execution of my program. So when you're compiling your program that has a main function, it's going to look like this. You have to pass this -g to everything that you're compiling. So with strings, we're going to have -g passed to strings array. We're going to have -g passed to strings list. We're going to have -g passed to the main function that we've got. I'm going to step through this now. I want to step through this with LLDB. I ran out of time to print this before class today, but I promise that I will print something that looks like this for you and bring it to class on Monday. When you are using a debugger, I would recommend that you find a cheat sheet. This one is GDB, which is another source level debugger. This is a GDB to LLDB mapping. I'm going to show you some commands in class, but I'd recommend that you have a cheat sheet for using this. In terms of assessment on this learning outcome, just to be clear, I'm not going to ask you to run a debugger in your final exam. I'm not going to ask you to do that. This is more of be able to use this to debug your own code at this point. So let's do this. We have code that crashes right now with segmentation faults specifically. My shell is printing out this program was terminated with signal sigsegv. Depending on the shell you're running, you might also just see the word segmentation fault, but the same thing is happening here. The strategy that I want to do with this is I want to run the debugger with no breakpoints. I just want to start my code running in the debugger's environment. I want to inspect the stack trace. So when you were running code in Java or Python and you had an exception, the exception would print out where the exception was raised, and it would put the entire call stack in that exception. We're able to get a backtrace or a stack trace in C with LLDB by using our debugger and using this BT command. This is going to tell us where ultimately the crash is happening. The crash might not be happening in our code, and so we're going to move around the call stack to find the place in our code where the crash is happening. Once you have an idea of where the crash is happening, we're going to add a breakpoint near the crash. A breakpoint is, I want you to stop on this line or on this function, and then restart the program. So step through each line in LLDB, and the command to do that is n. I'm going to do this in just a second, and we're able to print out the state of things. So let's head back to our terminal. We've got badcomputer.c here. I'm going to zoom in on this pane, and I'm going to recompile badcomputer.c. I'm going to recompile this with the -g flag. So I want to include debugging symbols. While I'm on the screen, I changed this to be the darker theme before class so that the terminal text effects would look cooler. Is this OK for reading? Should I change back to the lighter theme? Is it OK? Does anyone want to change back to lighter theme? Doesn't care? We're good? OK. I'm going to add -g here and recompile badcomputer. So -g again says include debugging symbols, include the source code. This is code that crashes, so I'm going to run LLDB on badcomputer. You might see this message that says module not found error, no module named LLDB.embedded interpreter. You may see this on Aviary. You may see it on your own system. You can safely ignore that message. LLDB is scriptable with Python. We're not doing scripting with Python, so that's kind of irrelevant. So you can configure LLDB to do stuff with Python. We're not doing that. So you can safely ignore that. That this says target create and current executable set to is enough. That's what we want to see to show that LLDB is running. The first thing I want to do here is run. So I'm going to do R for run. Run says I want you to start running this program. The debugger has now stopped. And it tells us the stop reason is signal sig_seg_v, invalid address. This, again, this means segmentation fault. This means that a segmentation fault has happened. I have to again say, take operating systems, because you'll learn what sig_seg_v actually means. You'll take a whole path through like your code trying to dereference something and get to the point of sig_seg_v or segmentation fault being printed to the terminal. And then eventually find out that segmentation fault is kind of a lie. But it is what it is. So our program has crashed here. I'm going to type in BT. BT is backtrace. What this is showing us is the call stack of functions that have been called where this code has crashed. Right now, we are in a file that is called libc.so. libc is the implementation of printf. This is where an actual function that's called printf is defined. I'm going to type L here. L is supposed to list. I'm going to do list. But there's nothing to list because we don't have the source code attached for libc. What I want to do is I want to move up the stack frames. This is where we've crashed. I want to move up and up and up into badcomputer.c, into main. So to move up a stack frame, I'm going to type up and press enter. This now tells me that I'm in libc.so.6, some other internal implementation of printf. I'm going to do up again, and now I'm in libc.so.6 in printf. And I'm going to go up one more time. And suddenly we can see that we've got code back. Here is a listing of the code. And what this is telling us right now is that on line 29 here, we've got this nice little arrow. On line 29, this is where the crash is actually happening. So we were able to get through substir, and then we got to printf, and now we're crashing in printf. So I want to set a breakpoint. I want to start inspecting the state of my code. I've seen where I've crashed. I want to start inspecting the state of my code just before the crash. So I'm going to do set a breakpoint on line 27. Got a breakpoint. I'm going to do R. I want to restart this program. It has crashed. It's not running code anymore, so I want to restart it. And I want it to stop executing when it gets to line 27. There's a running process, kill it and restart. Yes. The program is in this kind of like stuck state, but it's not able to proceed anymore. So I want to terminate it and restart. So yes. I set a breakpoint on line 27. And so now we have stopped execution here on line 27. At this point, I'm able to do things like inspect what variables are currently in scope. Frame variable is a command that I can give to LLDB, and what it will do is it will print out the value of the variables that are currently in scope. So it tells me that string here is of type pointer to char. This is the address that it has. So we've talked vaguely about this. This is an address that this variable has. And if we follow that address, the value that's at that address is all of these characters. Dest here is an array of 10 characters. And in this context, they are different things, but we filled it with null bytes. And on line 25, we can see that we did that. I want to move to the next line. I want to make LLDB run the line that I'm on and then stop at the next line. So I'm going to press N to do that. That line has finished, so we printed out to standard output this really long string, and now we're stopped just before running line 28. I want to inspect what the value of string is right now, so I can use P to print. P will print out the contents of a variable. String itself is a string in C, it's an array, so I can do things like print out character 8 of the string. So I can execute some basic expressions here. I want to go into this function, so I want to step into it. And the way that I can step into this function is S. So I've stopped just before calling subster, and I want to go into the subster execution. So S says step into. Now I've stepped into this function, and I can start to ask questions like frame variables, variable. So these are the variables that have been passed into this function that are declared. Here we've got 3 arguments that are being passed to this, in, start, and out. And then there's another variable that's declared later, but has got no value. So this is a stack frame that we're looking at. I'm going to step through each of these, so N to do that. And then a little shortcut here, I want to do N again, so I'm just going to press Enter on my keyboard, and that will go to the next line. So all of my assertions have passed. And now I'm going to start running through the loop that I've got in this function. I can't do stuff like p strlen in. I can't run functions, but I can cause expressions to run. So I can run expression strlen in, and then I have to cast it to int, and it will run that function for me. Oh, I wonder if p will work too then. Yes, it will. So we can do expression or p to run some functions and see what the value of that thing is. I want to step through the loop, and it's going to keep running over and over and over again. And as this is running, I can do things like, I want to see what the state of out is right now. I've copied some things into this, starting at whatever start was. So start was 2. In was, this is a really long thing. And then we're starting at the is in is this. Sorry, we're starting at the is in this. I don't really want to sit around and run through this loop. So what I'm going to do is I'm going to set another breakpoint on line 50. Line 50 is the next line where I've gone outside of this loop. So I'm going to do C now. I want to continue. I don't want to keep stepping through this line by line. C will get me to the next breakpoint. At this point, I'm going to print out out. And when I print out, we're getting most of what that string was with a bunch of extra stuff at the end because we haven't put the null byte on the string, so it doesn't know to stop printing there. If I do N one more time and then I do P out again, now it will terminate correctly. And then I can step over this and run this assertion again. In this case, we're still going to get segmentation fault because really specifically, if we look at this code, what we've done is allocated a 10-character long array to put 100 characters in, and we're writing past the stack. But we've been able to explore a little bit about using LLDB with this. Once we get into the segmentation fault, we're able to try to find the stuff that we're looking at. I'm going to stop for a second. If there's questions. Yeah. So the outputs that you see when you print things, especially with strings here, they are going to be very different from platform to platform. I also believe that, yes. Yeah, because of what this function is doing, it's kind of messed up in terms of it's overwriting stuff that's on the stack. At the very beginning, before we call the function, I'd expect that you'd see the same things as me, but as soon as we get into that function, stuff's going to start changing. It will diverge between what we've got. Even across different machines, like if you're running Windows Subsystem for Linux, I'd expect that you might have different output than what I'm seeing here. It might be identical, but it might be different. We've gone very far into undefined behavior territory. Yeah. But the lesson here is more about the commands and the debugger than the actual output that you're seeing. Yeah. Any other questions about this so far? Okay. What I would like to do next with this is I would like to walk the list that we've constructed. Sorry, did you have a question? Okay, yes, please ask the question. Sorry, I was looking the wrong way.
I don't know if it's just me, but it's telling me that my process, like my debugger process runs, but then it stops right away. So I can't run any of the backtrack functions or like lists or up or anything like that.
When it stops, what does it say when it stops? So that's kind of what I'm expecting this to do. You should be able to do BT potentially. Okay. Can you come and see me after class and we'll try and figure it out. Okay. So what I want to do now is I want to make some changes to our make file so that we can compile all of these things with debugging symbols. So I'm going to add -G to all of these, and I'm going to do this in one quick go. On most text editors, we have this convenient find and replace function with VS Code. I know that you've got that. You can hit Control H or Command H on your keyboard, and you'll get this find and replace thing. You can do the same thing with Vim, but it's, of course, keyboard driven. So to do this with Vim, I'm going to hit colon to enter a command. And what I'm going to say is %s / and then I'm going to type WALL. So now this is starting a find. And I want to replace this with WALL-G. And I'm going to put another slash, and I'm going to say G for global on all lines, not just the one that I'm looking at right now. And if I do that, I've added -G to all of these things. So very quickly, that's %s, that says search, / the thing I'm searching for, another / the thing I want to replace it with, another / and then G for global. If you don't put the G for global, it will just do the first one that it finds. So I've replaced all of these with -G. And now I'm going to quit this. I'm going to write it and quit. I'm going to make clean because I have all these files in this directory right now, but they have been compiled without debugging symbols. So I'm going to make clean, and then I'm going to make again to recompile everything with debugging symbols. If you forget to put -G here on something like strings list, and then what results in a .o file, what you're going to find, or if you forget to put -G at all, what you're going to find is that you'll see assembly language instructions when you run the debugger. So it's not able to map the instructions back to the source code that you've got. So I'm going to run LLDB with strings. I'm going to do main strings, main list. I'm going to run this on main list. And I'm going to break on main. So in the last example, we were setting breakpoints on specific lines of code, but we can also break on an entry to a function. So I'm going to break on the entry to main here, and then I'm going to run. And the first thing that we're stopping at is the first thing that happens to be in our main function that's not just a declaration. What I want to do here is I want to step into this because I want to start walking a list. I want to start walking a list. So I'm going to step into make string. And now we're in strings list.c. So as I stepped from line 13, I've now moved into strings list.c. I'm going to hit n a couple times. I want to skip past these. So I hit n once, press enter, and I'm just hitting enter again to not have to type n every time. And what I'm going to start doing here is I want to print out my string. So I'm going to use p. If I just p my string, it prints out just the address of the thing, which is not super helpful. I want to see what's inside that. So to print out what's inside of a structure, I'll do print, p for print, and then I will dereference this. So an asterisk in front of it. And then I can see this is the contents of the structure that I'm looking at. I'm going to step to the next line, and then I'm going to step into insert end. Now I'm at insert end. Insert end has 2 arguments that are being passed to it, and then a couple of things that have been declared. We've got to add the pointer string. We've got new node, cur, and prev, and all of these have kind of random looking values because they haven't actually been initialized with anything yet. And what I'm going to do now is insert to the head of the list. Head is equal to new node. I'm going to print out s. Its head is now this thing. So I want to see what's in that node. So I'm going to print out s at head. This still prints out just the address. So I need to dereference all of this. So put that asterisk in front of it. If I do p asterisk s head, now I can see what's inside the node that's referred to by my string object. I'm going to hit next again, next again, next again. Now we're at the end. We've gone back to make string. We're at the loop entry point again. We're going to be checking to see if I is less than numchars. So I'll hit n, and now I'm going to enter insert to end one more time. If I print out s, we've still got a single head. If I print out s head, we still have something that points at null. I'm going to hit n one more time. I'm going to do check string here once. I'm going to insert the node. So now we're in that other case. ps, s is not null, so I'm going to change cur to that. I'm going to find the end of the list. I found it. I'm going to insert the new node. I'm going to print out s right now. If I print out s head, I get something that has a next. If I print out s head next, I can see what the next node in that list is. So I can use my debugger to kind of go deep into this object structure, this linked object structure, to help me better understand what the state of things is. I can also run some code. I'm going to run some code. I'm going to say expression s head is equal to null. So just after inserting that node, I have basically said that my string's length is 1, but head points at null. And if we think back to our invariant, this is an invalid string now. I've forced this thing to become invalid. So I'm going to step over the next line, and now we're getting to check string. I'm going to run n one more time, and check string is running all of those assertions. So there's a bunch of assertions in here that are checking to see whether or not our string is valid. Here, we're getting killed again. We've got this assertion failure. S length is equal to count failed because our loop never enters. We're never getting into that loop that's counting up the nodes that we've got in the list. So count is 0, S length is 1. We can use the same tools that we had with segmentation fault here. So I can do things like backtrace. Now we're kind of deep inside of libc, but if I go up, and 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 I go up, I can get back to my code. So here I'm in main list check string in strings list.c on line 38, and this is the specific assertion that failed. I can run frame variable to see what the values of things are that have been given to me. And I can do things like print out the contents of the string. And yeah, that's definitely an invalid string in terms of what we have defined our invariant to be. Using a debugger like this is a pretty powerful tool. It stops us from having to execute all this stuff in our head. That's important to be able to do, but letting something help us with that is a lot nicer than having to whip out pen and paper every time you want to try and figure out why your code is crashing. All right, any questions about this? We good? We're good. Okay, good. So I know last time, yesterday, you said that when you were trying to do VS Code with Java, it didn't always work or it didn't get configured. This, I hope, is going to be a little bit more reliable for you in terms of it will work. And I will try to make sure that it works for you too. It will work. It will definitely work on Aviary. If you try to do this stuff on Aviary, you'll definitely be able to get through some of this stuff. All right. Let's take a step back to this idea of structures and private and public in C. Right now, we're in a state where everything in C is effectively public by default. So we talked about structures. They're this bag of properties. We've listed all the properties. They don't have access modifiers. If you have the ability to see the full definition of the struct, you can access all the properties, and there's nothing stopping you from doing that. We're trying to hide the implementation details of a structure by only giving you a type def in a header so that someone cannot see all of the properties of a structure, but everything is still effectively public by default. Our string interface has an interface and two implementations of that interface. Everything that we consider to be a public function is in the header file. So right now we've got make string, char at, and destroy string. These are the public operations that I'd want someone using my strings library to be able to call as a function. We've got our private function implementations and public implementations in our .c files. So we've got string arrays and we've got string list. Both of those have implementations of all the public functions that are defined in the .h, but we have other stuff. We have a function that's called insert end. We have a function that's called check string. These are not defined in my public interface. Can I still call these functions even though they're not defined in my public interface? The answer is yes. Yes, the answer is yes. So let's see. I'm going to get out of LLDB here. I'm going to open up strings list.c. In strings list, we have this function that's called checkstring. This has not been defined in our public interface. This is not in strings.h. I'm going to open up main.c. And I've included strings.h. So we've got forward declarations for all of the public functions. I'm going to create this instance of my string, and then I'm just going to call checkstring. I'm going to quit strings_list.c. I'm going to make. And we get warnings. We are definitely getting warnings here. Implicit declaration of function checkstring, but it produced a binary file. It produced a program that I am able to run. If I run this program, I'm going to make one last change here. I want to show that we're actually running this because checkstring right now does not do anything. So I'm going to add here to checkstring in checkstring. I'm going to make this one more time. We've got this warning that it's not been declared, but we're calling it. And if I run, main list, we can call it. I'm going to do this. I'm going to say printf just before check string and main. I'm going to printf just after. I'm going to recompile this, make. I'm going to run it again. And I was able to call it. It got called a lot more times before that internally, but this private function that I've got, I was able to just call it. Nothing stopped me from doing that. I got warnings, but I can also make that go away by just forward declaring that. Void check string. I'm going to check what the actual declaration of this is. Check string const string s. I'll forward declare it. I'll quit strings list. I'll make it again. And now I'm not even getting any warnings. I have a question for you to think about. Should I be able to call that invariant? You don't need an answer right now. Just think about it. Quick thumbs up, thumbs down. I should be able to call it yes, thumbs up. I should not be able to call it thumbs down, no. 1, 2, 3, everyone thumbs up, thumbs down. Whether you're paying attention or not, thumbs up, thumbs down. Quick, quick, thumbs up, thumbs down. Thumbs up, thumbs down. Thumbs up, thumbs down. Which one? Thumbs up or thumbs down? Thumbs up, okay. Yeah, thumbs down. It's thumbs down, okay. It's thumbs down. Yes. The invariant is private to my implementation. And it's private to my implementation because if I go back into strings list and I go back into strings array, the contents of check string are different for each of these. The implementation here of check string really highly depends on the implementation that I have for this thing. Me, as a user of this library, should not have the ability to call private functions. In Java, we've got that cool keyword private that says, no, you can't even compile this code if something is marked as private. In C, we have another word, but I'm going to take a tangent. What does static mean in Java? I don't need an answer from you. I want you to jog your 1020 memory right now. What does static even mean in Java? It belongs to the class. Yes, I hear someone mumbling it belongs to the class. Thank you for the mumble. That was a correct mumble. Yes, it belongs to the class. When I say public static void main, what I'm saying is the enclosing class, the class definition itself has this method. This is not an object thing. I cannot make changes to the instance of this class with this method. It's attached to the class. When I say public static final variable name, that variable name is attached to the class. It's not attached to an instance of the class. It's attached to the whole thing. Static in Java means I've got a method or a variable, and this method or variable is attached to the class. In C, static means per file private. We can use static on either variables or functions. And when we put static on a variable or function, it means that I can only call it from within the file where that thing has been defined. This is our private keyword in C. And going forward, so not for assignment 2, but for assignment 3, when you have private functions, they should be marked as private with the static keyword. I'm going to quickly go through here and amend strings.c. I'm going to quit stringsArray.c, and I'm going to make a change here in stringslist.c to add this static keyword. That's the one word change that I'm making to this. I'm going to delete this printf. I don't actually want to print a bunch of stuff out every single time my invariant is called. I'm going to try to make this one more time. And when I make this now main.c, when we get to trying to compile main.c with stringslist.o, there's an undefined reference to this check string function, even though I forward declared it. It just doesn't exist anymore. I'm going to go back to stringslist.c. Sorry, I'm going to go to main.c. And I'm going to comment each of these out because it's preventing my code from compiling now. So I've marked this as static. I'm not able to call it anymore. There's one weird trick that we can do with this. Do you have a question? OK, sorry. There's one weird trick that we can do with this. And so I'm going to do this, this one little thing here. The one weird trick that we can do with static in C is I'm going to make a new file here. So I'm going to copy my template to main static.c. And I'm going to edit main static. And I'm going to add a new function here called counter. Counter doesn't take any arguments. I'm going to declare the function above, and I'm going to define it down here. Takes no arguments. I'm going to say static int counter equals 0. And then inside of this, I'm going to say counter plus plus. And then I'm going to say printf counter is %d. In my main function, I'm going to call counter. Oh, I'm going to call this something else. I'll just call it count inside the function. I'm going to close stringslist.c, and I'm going to compile my main static. If I compile this and run it, I called it one time, and so the output is remarkably surprising in that it prints that counter is 1. I'm going to call this 2 times. I'm going to compile it again, and I'm going to run it, and I'm going to call this 3 times. I'm going to compile it, and I'm going to run it, and I'm going to call it 4 times. To really drive my point home here, static int count is now a variable whose scope is inside this function. So counter is a function. We've got this variable that's called count. It's only available inside that function. But when I mark this as a per file variable, it's scoped inside here, but it retains its value every time I call the function. So if I repeatedly call this function over and over again, static count never gets reinitialized after the first time it's been called. This line here only happens once. I'll add a comment. Initialization only happens once. The first time the function is called for static variables in a function. That initialization happens only one time, and then it retains its value every time after I call it. I'm going to take a little step back here. In the very first assignment, I told you don't use this function strtoke. I still stand by that. I don't like to use strtoke because I find that its semantics are kind of confusing. I'm going to zoom in here. What strtoke takes is a string and then a delimiter. The string is the first thing that you're passing to it. The delimiter is kind of like with split in Java, you put a space character, something like that. This is the thing that I want you to separate this string on. The way that strtoke works is that the first time you call it, you pass it the string. The next time you call it, you pass null. But it gives you the next token in the string that you passed to it the first time. And the way that it accomplishes that internally is it uses this static marker on the string that's been passed to it the first time. This function keeps state. That part is not, it's not like super confusing. The really confusing part about strtoke is that the string you pass into it gets destroyed as it tokenizes the string because it goes through and it inserts null bytes where the delimiter is. So if you pass it strtoke a string and then the space, every time it finds a space, it's going to replace that in the string you passed it with the null byte. So if you have that original string, it's going to just look like the first word every time you try to use it later because it's inserting this null byte. It's useful, but it's super weird and kind of confusing because of the state capturing and because it's destroying the string that you're passing to it. All right, this is the end of static. As I said, in assignment 3, when you have invariants in your code, they should be marked as static in your code. They should not be exposed to the outside world. I'm not going to do this because I don't want you to do it. Specifically that, don't do that. I don't want you to do this. There's a keyword in C that we can use called extern that will allow us to share information between units. So we'll have one .c file and another .c file, and we can have a single variable that's shared between them and scoped between them. I don't want you to do that. And I'm going to skip right to the end here. Don't do it because it's exposing implementation details. You've got 2 different things that are unrelated, possibly sharing information. And this is a keyword that's called high coupling. We will talk about coupling very soon, but not today. So at this point, what you should be able to do is use a source level debugger such as LLDB to inspect program state and step through code line by line to determine the cause of errors in a program. You should also be able to define the implementation of an ADT with a private data structure, really specifically using this static keyword for hiding private functions in C so that they cannot be called by anyone else. That's it for today. I hope that you all have a great weekend when you get to it, and I will see you all next week. Bye, everyone.